Here we go with the Chapter 6 required homework problems. We'll start off with the questions, and the first question is question number 2, asking if a man pushes very hard for several seconds on a heavy rock, but the rock does not budge, has the man done any work on the rock? And we have to explain. Well, we know that work is equal to the force applied multiplied by the distance over which it's applied. And in this case, since the rock doesn't move, the distance is 0. So if the distance is 0 meters, it doesn't matter what the force is, because work is force times distance, and if distance is 0, anything times 0 is 0. So there's 0 joules of work done if we don't move the rock. Next, question 3 talks about a box or a wooden block with a string tied to it, and there's a force pulling the string, and it's pulled through some distance d, and it says, does the force applied via the string do work on the block? Well, there is a force, and it's being applied to move the block through a distance, so yes. But, as part B is asking, not all of the force is in the direction of the distance. Some of this force is pulling the block up, and some of the force is pulling the block in the direction the distance is going. This part that's going in the direction of the displacement, that component is doing work. Only that component. The part that's pulling up doesn't. Next is question 15, where we are lifting a box up off of the ground. It says that we're moving the box off the floor up to a tabletop, but we don't speed it up as we're going up, so there's no acceleration, but it is lifted. So there's 2 different ways to look at that. So the question's asking, is work done on the box? And if so, what happens to the energy that's added to the system? So we know that we are lifting the box up. We're giving the box some height above the ground. And if we're giving the box some height, we're giving it potential energy. And we know that work is going to equal the change in energy of the system. So by that logic, since we are giving it potential energy, then yes, work is being done. You could also look at it like this. In order to lift it, even if you're not speeding it up, you still have to overcome the force of gravity, which means you have to apply a force at least equal to the force of gravity. So we're applying a force to lift it up some distance. In this case, our distance is the height that we're lifting it up. So force times distance equals the work done. And the second part, what's happening to the energy that's being input? It's being added to the potential energy of the box. So we're changing the energy of the box by adding potential energy. In question 22, we are pulling a pendulum back, as shown here. It's initially hanging straight down. We pull it back so it's raised up some height above the original. So there's 3 parts to this question. The first one says, what form of energy is added to the system prior to letting it go? So we pull it back and we're holding it back at this position. It's higher than it was, so we're adding potential energy to the system before we let it go. Once we let it go, that potential energy starts turning into kinetic energy as it goes back down towards that lowest possible point. So question B says, at what point is the motion of the pendulum, in what point in the motion of the pendulum is the kinetic energy greatest? And the point when it's the greatest kinetic energy is when the potential energy is the lowest, because the potential energy is converted into kinetic. And the point when the kinetic energy is the highest and the potential energy is the lowest is that initial bottom point. So the lowest point on the pendulum swing. And then part C, at what point is the potential energy the greatest? And again, that's when the height is the highest. There's 2 points when, assuming that we're not losing energy to the environment, ignoring the air resistance. So when it's at the peak of its swing, the change in height is the highest. the kinetic energy is the lowest. It comes to a stop before swinging back the other way. So at those 2 points, here, let me change color, here and here, the potential energy is the highest. Question number 33 describes shooting a dart from a spring-loaded gun. That's my drawing of the spring-loaded gun right here. And describe the energy at the various points of that that process. We're shooting the spring-loaded dart gun straight up into the air at a target up on the ceiling. So what type of energy does it have? Initially, before the gun is fired, all of the energy, so right here, energy is potential energy due to the elastic potential energy in the spring, the coiled spring. We compressed the spring, we gave it elastic potential energy. When the gun is fired, the spring is released, it pushes the dart up, it does work on the dart, giving it energy of motion. At the bottom point here, right before it's leaving the end of the gun, before it goes up towards the target on the ceiling, all of its energy is kinetic energy, because it's the energy of motion. Its height at the bottom is 0, so it doesn't have gravitational potential energy yet, but the spring has done work on it to give it energy of motion. It's got kinetic energy. Now at some point in the middle, we have our dart, and here we have both kinetic energy, because it's still moving up, but we also have gravitational potential energy. So as it's moving up, the kinetic energy is decreasing and the potential energy is increasing until it gets to the top point, when all of the energy is gravitational potential energy. All right, on to the exercises. Exercise 3 says we have a force of 60 newtons, and we're pushing a chair across a room, and in doing so we are doing work. 300 joules of work is done. It says how far does it go, so we want to know the displacement of the chair, and that'll be in meters. So we know work equals force times the displacement, and actually we can solve that for the displacement. So displacement equals work divided by the force, which is 300 joules divided by 60 newtons, and we end up with a displacement of 5 meters. Exercise 5 has 3 parts. We have a box, and we're dragging it, a crate. We're dragging it with a force of 50 newtons, and that 50 newtons is at some angle, which means that not all of the force is pulling in the direction of the displacement. Some of it is pulling up. So we have 30 newtons of force pulling up and 40 newtons of force pulling to the right, and we move the box 4 meters to the right. So, part A says, what is the work done by the horizontal component? Horizontal is the left and right component. So the 40 newtons. So we know the force is 40 newtons. We know the displacement to the right is equal to 4 meters, and work equals force times displacement, or 40 times 4, which gives us 160 joules of work. Part B says, what is the work done by the vertical component? So work equals force in the vertical direction is 30 newtons. But what's the displacement in the vertical, in the up and down? Is 0 meters. So 0 times 30 is 0 joules of work. And part C, what is the total work done? Well, since no work is done in the up and down, the only work done, the only displacement, the only distance traveled is in the horizontal. So the total work done is 160 joules. Exercise 10 presents a spring, and we have stretched the spring by 0.2 meters or 20 centimeters, and to do so required 40 joules of work. So we did work of 40 joules in order to stretch that spring out the 0.2 meters. So part A asks us, what is the increase in the potential energy of the spring? Now recall that work equals change in energy, and we aren't changing any other type of energy. Once we have compressed or stretched the spring, it's all elastic potential energy, so the change in energy is going to equal the work done. Therefore, the increase in potential energy in the spring is going to equal the work done. So potential energy of the spring, the elastic potential energy, is going to equal 40 joules. Now, part B is saying, what is the value of the spring constant? Now, recall that potential energy of a spring, the elastic potential energy, is 1/2 kx squared, where k is the spring constant, and x is the amount that we either stretch or compress the spring. So we know the amount of stretch or compression, we know the potential energy, we just have to solve this equation for k. So we can multiply the two up, and we end up with 2 times pe, and then divide both sides by x squared, and we end up with k equals 2 times pe divided by x squared. And potential energy is 40 joules, and the distance is 0.2, and we square that 0.2, and we end up with a spring constant of 2,000, and I'm not going to be too strict about this, but the unit will be newtons per meter. I don't think we talked about that in class, but that's what it is. In exercise 12, we have another pendulum, and we've pulled it back to some height and released it, and when it gets to the bottom, when it has its maximum kinetic energy and minimum potential energy, it has a velocity of 4 meters per second. And we are also given that the pendulum bob is 0.2 kilograms, so that's the mass of the pendulum. So part A is asking, what is the kinetic energy at the low point? And since all of the energy is kinetic and we know the mass and velocity at that point, that's not too hard to do. We can just use our kinetic energy equation, 1/2 the mass times the velocity squared. So 1/2 times 0.2 times 4 squared, or 1/2 times 0.2 times 16, and that's going to equal 1.6 joules. All right, part B asks us, so we're ignoring air resistance and friction of the pendulum. So we're assuming that all of the energy is, all the mechanical energy is conserved, none of it's lost as heat. How high above that bottom point is it going to go when it goes up on the other side? What's the highest point of the pendulum? So we're trying to find this height right here, h, the difference in height between the bottom and the top. Now, if we ignore any energy lost to the environment as heat, then the kinetic energy at the bottom is going to equal the potential energy, the gravitational potential energy at the top. And we know the kinetic energy at the bottom is 1.6 joules, and that's going to equal the potential energy at the top, which is the mass of the pendulum times the acceleration due to gravity times the height. What we're trying to solve for here is height, so we'll divide mg to the other side, and height equals 1.6 joules divided by the mass of the pendulum times the acceleration due to gravity. So that bottom part is 0.2 times 9.8. So 1.6 divided by 0.2 times 9.8. And we end up with a height of 0.82 meters. lastly, we have a synthesis problem. We have a block or a box here that's being acted upon by two horizontal forces. One is a pull to the right of 5 newtons, and the other is a frictional force of 2 newtons opposing that motion. The mass of the block is 0.25 kilograms, and it's moving through a distance of 1.5 meters. So, part A asks what the work done by the 5 Newton force is. So, work equals force times the displacement, and we know the force is 5 newtons, and the displacement is 1.5 meters, and that would give us a work of 7.5 joules. What is the work done by the net force acting on the box? So we have F net, which is going to equal the work to the right minus the work to the left. So 5 newtons minus 3 newtons. Oops, sorry, 5 newtons minus 2 newtons. Sorry about that, because 2 newtons here. My handwriting isn't very good, but 5 minus 2 is 3 newtons of net force. And to find the work done by that net force, we need that net force, which is 3 newtons multiplied by the distance, or the displacement, sorry, of 1.5 meters, and that will give us a work of 4.5 joules. All right, which of these two values should you use to find the increase in kinetic energy of the block, and explain? All right, so this is a conceptual question, not really a mathematical question, but what does the 5 newtons want to do? It's trying to increase the kinetic energy. It's giving it more kinetic energy. Now the frictional force that's opposing the motion, that 2 newtons backwards, is reducing that kinetic energy and converting it into thermal energy of the environment. So if we want to find the total kinetic energy, we take the 5 newtons that's giving it kinetic energy and we reduce it by the 2 newtons that's taking away the kinetic energy, which will give us the total kinetic energy in the end. So the 5 newtons is increasing the kinetic energy, the 2 newtons is taking that kinetic energy and converting it into thermal energy, which brings us to D, what happens to the energy added to the system via the work done by the 5 newtons? Well, it's reduced because the 2 newtons of frictional force is converting it to thermal energy. So can it all be accounted for? Yes, it can be accounted for when you consider all of the different types of energy in the system. So it's not mechanical energy anymore, it's now thermal energy, and some of it is thermal energy and some of it is actually still kinetic. Which brings us to letter E. If the block started from rest, from velocity equals 0 initially, what is the kinetic energy and the velocity at the end of the 1.5 meters of motion? So what do we know? We know that work done equals the change in energy, and we know that in order to find how much the kinetic energy has changed, we're going to use the net force. So we know that the net force has done 4.5 joules of work. So that means we have an increase of 4.5 joules of kinetic energy. So it goes from 0 at rest to 4.5 joules. So if the kinetic energy at the end is 4.5 joules, and I know the mass, I can solve for the velocity. Kinetic energy equals 1/2 mv squared, and I can solve that equation for v. Multiply the 2 up, so 2 times the kinetic energy divided by the m, and then take the square root, and that's going to equal the velocity. And now I can just plug in my numbers. 2 times 4.5, and then divide that number by 0.25, then take the square root. And I end up with a velocity of 6 meters per second. And that's it.